don't know what you think yet. I happen to think the operator methods are very interesting, and but sometimes they just don't work very well. And here's an example. I would say you would do this by method of undetermined coefficients a heck of a lot faster than you would with an operator. And here's why. Because y double prime plus 3y prime plus 5y equals to 4x minus 7. So the polynomial operator is d squared plus 3d plus 5 operating on y equals to 4x minus 7. So y particular will be 1 over d squared plus 3d plus 5 operating on 4x minus 7. Now the right side, this doesn't matter so much. This is the problem here, because it doesn't factor easily. And if it doesn't factor easily, what kind of expansion can I use for this fraction? You know, the denominator is a quadratic, irreducible quadratic equation, and so I don't have a ready-made expansion for that, infinite series expansion. Well, there is one, and I can show you how it can be done, because this can be factored, but it's pretty ugly. So bear with me. I want you to see this. What I need to do is to complete the square on this polynomial. And complete the square, I take half of the linear coefficient, 3. So I have d squared plus 3d. Half of that coefficient is 3 halves. So I add 3 halves squared and subtract 3 halves squared, and I still have the plus 5. Alright, so what do we just do? When you complete the square, I don't know if you remember this, on a quadratic, you take half the linear coefficient, would be 3 halves, and you square it. So I added parentheses 3 halves squared to my denominator. In order to balance it out, I also have to subtract it, and I still have the plus 5 to deal with. Great. So now this becomes 1 over, this part right here is a perfect square polynomial. What is it? Well, it's d plus 3 halves squared. Okay, and then here we've got minus 9/4 plus 5. And what's that equal to? Minus 9/4 plus 5 would be 11/4. 5 is 20/4 minus 9, 11/4. So I have plus 11/4. Now then, that's the difference of two squares. It can be factored. So it's 1 over d plus 3 halves squared, first power, d plus 3 halves, and then minus the square root of 11 over 2i times, I tell you what, that looks pretty ugly. Let me go up and do a little erasing and I'll write it a little more clearly. Okay, we'll try this again. I'm going to think of this as a difference of two squares. And when I factor it that way, it's d plus 3 halves minus this square root, square root of 11 over the square root of 4, that's square root of 11 over 2, times I, and then times the conjugate, d plus 3 halves, and then plus square root of 11 over 2i. So now you can go back and multiply this mess out, and you'll get this, because we'll have d plus 3 halves squared here. We'll have a positive term and a negative term, which will cancel each other entirely. And then when I multiply this out, I've got minus 11/4 times I squared. That's going to end up being plus 11/4. So we factor this into this big mess. Let me put my 1 over the center here. And now we get to operate on 4x minus 7. Well, it can be done. It can be done. I'm kind of taking this to its almost absurd extreme, except I'm not going to finish the problem because I'm not that motivated. But y particular will be 1 over d plus 3 minus the square root of 11I over 2 d plus 3 plus the square root of 11I over 2 operating on 4x minus 7. There we go. So we have d plus and minus a complex number, which I think we could have gotten by just solving a quadratic equation rather than completing the square. We could have done it that way. But the idea is that this is pretty messy. You know, if we did a partial fraction expansion, can be done. Hold on, telephone. Well, that was my my stepson calling about my my lawnmower, which he's fixing. He's a repairman, and so kind of lost my place here. But as you can see, if I broke this up first into 1 over this expression and formed an infinite series expansion, it'd be very messy. Okay, because we have complex numbers, and then we did the same here, did it again, very messy. So not a good plan, and probably even worse would be to try to do a partial fraction expansion. So in this case, I think it's kind of obvious that operators do not do well on this particular problem. If this polynomial doesn't factor into products of linear factors, and then I would say forget it, use method of undetermined coefficients. Okay, so which will be a lot faster to solve. So anyway, I wanted to look at this and say that all is not great in paradise on operators. Sometimes they just don't work very well. Okay, but sometimes they're very advantageous. So we'll get into those issues as we plow through all the operators. All right. Well, next let's go on to different kinds of right-hand sides.